started. So today, I'm very happy to have visiting us Piero Madau. Piero works on many diverse, broad range of topics in astrophysics, ranging from the early universe, galaxy formation, the ionizing UV background, early galaxy formation, reionization, 21 centimeter, gamma ray bursts, and a whole other list of topics. Piero got his PhD at the International School for Advanced Studies in Trieste, Italy. Went on to Caltech, spent time at Johns Hopkins and Space Telescope Science Institute, and ever since 2000 he's been a professor at UC Santa Cruz. And today he'll tell us what's wrong with the dwarf.
Yeah, with a question mark. Thank you. It's a pleasure to be here. I have a long history with some of the faculty of this place. Chris and Norm, we overlap at Caltech long time ago. And, you know, I remember scientific discussion, but most of all I remember we used to play pool every day after lunch.
Oh, that?
Yeah. Oh, you forgot about that. That's where we spend most of the time as postdoc, playing pool. And I don't remember who was winning, actually. I think it was Chuck. It was not you, and it wasn't me. I think it was Chuck Evans winning most of the time. Anyway, it's a pleasure to be back. So I'll talk about dwarf galaxies. Dwarf galaxies are in the news more often than any other Hubble type. Okay, and the reason is for about 20 years or so, they have defined our understanding of the mapping between dark matter halos and their baryonic component. And in particular, they've also challenged simulations of structure formation in lambda CDM. And there are basically two types of dwarf galaxy problems. One is an abundance mismatch, which you see in the field as well as in the galactic halo. And it's quickly summarized by just looking at the mass function of dark matter halos versus the stellar mass function of galaxies today. If you compare the two, you will realize that dwarfs are supposed to be forming stars with an efficiency, given their halo mass, that is a factor of 10, 1 order of magnitude less than what's typical for Milky Way galaxies. Okay, they form stars with low efficiencies. That has been extremely difficult to reproduce in numerical simulations, where you have plenty of time for the gas, without feedback in particular, for gas to cool down in those halo and form stars. In the Milky Way, this takes the form of a missing satellite problems, plenty of satellites, of subhalos in N-body simulations of Milky Way type of structures, not very many dwarf satellites, and that means that a lot of those, in fact, dark matter clumps are supposed to be dark to form stars with a low efficiency, and the issue is, why is that the case? There is another problem which is quite different, and it's a structural problem. It's a structural mismatch. Dwarf galaxies have dark matter profile. Here is the slope of the density profile as a function of radius within a few kiloparsec from the center. And typical dwarfs have chord profile. Their density profile as a core, which is a nearly constant density profile, as opposed to what you get in collisionless simulations and body-only simulation, where those dark matter profiles are cuspy. Okay, typically an NFW profile with a slope of -1. This is the cusp core problem, again seen in the field as well as in a couple of luminous dwarfs, dwarf satellites of the Milky Way, as I'm going to show you later. In the Milky Way, this takes a different name. It's called the too big to fail problem. And I think it's a similar problem than this. And basically, again, it's the idea that if you do N-body simulation of a Milky Way type of halo, and you plot the circular velocity profile as a function of radius, say within the inner 1 kiloparsec of the most massive subhalos, okay, that you see in those N-body simulations, and you compare that with the most luminous dwarf spheroidals in the Milky Way, what you find is that dwarf spheroidals are not as dense as N-body simulation would predict. And because it is unlikely that these subhalos are totally dark, they should have a counterpart, a luminous counterpart, hence the name too big to fail. They can't be failing, they should be forming stars. Why are their central densities not as dense as we see in the satellite of the Milky Way? So why all the hype about dwarfs? Let me remind you, dwarf galaxies are cosmic dark matter laboratories. They probe the power spectrum on small scales, and then they offer a unique test of the particle nature of the dark matter. This is the mass variance versus mass from a recent set of simulations run by Ville last year, which shows that, in fact, you can use the Lamin alpha forest to put some constraint on the mass of a candidate warm dark matter particle, which must be greater than 3.3 keV or so, corresponding to a free streaming mass of about 10 to the 8 solar masses or so. Okay? So the idea is, by studying systems on this mass scale, we might be able to constrain the mass of the dark matter particle if it's that low. Dwarf galaxies are also the champions of the epoch of first light. They are the first generation of cosmic structure that goes nonlinear, and so they are believed to be responsible for the reionization history and chemical enrichment of the early universe. And finally, they are the building block of massive galaxies, and so their remnants provide a powerful test of the assembly of cosmic structure. This is a simulation run a few years ago. It's ARIS. It's the simulation of Milky Way halo, and what you're seeing here is the distribution of particles in that halo, in that massive halos, as that halos, in fact, is built by the accretion of satellites. This is in configuration space. This is in phase space. This is radial velocities versus distance, and you can see this, the label here, the velocity goes from plus 400 to minus 400 here, and the distance is 200 kpc or so. And what you saw, let me run it again. This was the entire assemble of the halo, and here we are just zooming in into one of those satellites. All the rest has been done black, and you see the tidal disruption of a satellite that is accreted at a redshift of 0.77. It's got an initial mass of close 10 to the 10 solar masses or so, so it's a dwarf galaxies. And the end of the process, it ends up, it's still a bound structure, it's not totally disrupted, and has got a final mass that is, say, 0.3% of the mass at infall. And again, you see the streams in phase space produced by the accretion of that satellite. Now, I'm sure you've seen some of these videos of radio simulation. If you're not particularly impressed by this, you should be, because I'm not plotting dark matter particles. These are stars. Okay, the new generation of simulation, which I'm going to describe, and some of those are running in-house, so you might be familiar with this. But the new generation of simulation is able to simulate the formation of a Milky Way type of system in a fully cosmological setting from cosmological initial condition with gas and with a SPH technique, for example. We can have as many, put in as many as 13 million of SPH particles. Okay, so this particular simulation, it's a hydro simulation, which started at redshift 100 or so, and it's still one of the best simulations of a Milky Way type of galaxies system, and it was run down to z equals 0 with a total of about 26 million particles. Okay, and you see here the formation of the stellar halo, which we can study in detail. I'm just, it's a small digression here. Let me just show you how well this, what we can do with this type of simulation. And again, these are our simulation, but it's representative of a bunch of fancy, high-tech, high-resolution simulations that have been running over the last couple of years or so. once you have a stellar halo simulated, you can do a mock SDSS, a slow digital sky survey for halo star. You put an observer at 8.5 kiloparsec, and you change the azimuthal angle around, and you can make heat maps of the predicted line of sight velocity dispersion as a function of distance of all the stars in that simulated halo. And you can compare that with observations, because we are accumulating observation, for example, from the SDSS halo sample here for blue horizontal branch stars at extremely large distance, okay, like 100 kiloparsec away. And those are the points here from a bunch of papers from Cruz and Dizon over the last few years. Those are the points here, and that's the heat map of the simulation for a halo that has got a mass of about 8 × 10⁻11 solar masses, okay? These are expensive simulations. We don't run them 10 times and fiddle with them in order to fit the data, okay? It took about 6 months to run that simulation. So we don't have the luxury of a semi-analytical model where you can keep running and change the parameter and adjust them. It's just to show you what the new simulations are able to do and how much we can learn about the formation of a stellar halo with the new satellite Gaia that is accumulating data. Back to dwarfs. An attractive solution to the dwarf galaxy problem is, of course, baryons. I mean, you can change the properties of the dark matter, and that's perhaps a more radical solution. But you know that the discrepancies are happening on scales that are small enough where baryons can have an impact. And so until recently, any direct effect of the baryonic component of the dark matter was limited to a minor adiabatic correction, where gas would fall in and steepen the dark matter profile. Okay? And so the idea was that baryonic processes would modulate the star formation rate without changing the underlying dark matter structure. Okay? Or not changing it by much, basically change the profile, steepen the profile a little bit in the inner region. The picture has recently been subverted. Spectroscopic observations have been leading this change. They've shown the ubiquity of galaxy scale outflows. This is a plot from Crystal Martin showing the blue shifted velocity of lines that are spectroscopically detected as a function of star formation rate in those systems. And you see the evidence, there is evidence in the data for outflows at a few hundred kilometers per second or above 100 kilometers per second, even in dwarf galaxies that are forming stars at a rate of 0.1 solar masses per year or so. Okay? So if there are outflows and baryons are being driven away from the center by star formation, for example, or supernova feedback, then you would expect these outflows, in fact, to have an impact on the density profile of the dark matter. Incidentally, I didn't say that, but feel free to interrupt anytime, okay? Let's keep this informal and stop me if there is something you want to be clarified. So the idea is, or the question that people have been exploring recently is, can supernova feedback fix both the dark matter density in the center of dwarfs, as well as explain the low star formation efficiencies? Okay? And ideally, again, you would use a combination of semi-analytic technique and simulations. The problem from the simulation point of view is that capturing the baryonic and feedback processes that regulate the metabolisms of the dwarf galaxies, the ingestion of gas, the formation of stars, and the ejection of gas from galactic winds require cosmological hydrosimulation of extremely high dynamic range. Gas in such low metallicity system does not settle into a thin cold disk because it can't cool fast enough or to low temperatures when the metallicity is that low. And so that means that, and the combination of the shallow potential well will make the interstellar medium of those systems more prone to disruption from energetic supernovae, and that's a process that you should be able to simulate. Star formation may proceed in a bursty manner that is different from that of larger mass spiral. And there is evidence for that in the observations. These are observations of a couple of years ago, a few years ago, from candles Candles has been looking at a bunch of small galaxies. These are small stellar mass systems, about 10 to the 8 solar masses or so, at a ratio of 1.5 about, and all these systems reveal extremely high equivalent width of oxygen-3, which is something that you can reproduce only if the specific star formation rate, the amount of star formation produced per stellar mass in those systems, the specific star formation rate is extremely high. It's about 50 giga-year minus 1 or so, which is 50 times higher than what's typical for the Milky Way. Okay, a Milky Way type of system is forming stars at a constant, relatively low rate. These dwarfs are forming stars in a bursty manner. Burst of star formation, high star formation rate for a short amount of time, then nothing, then another burst. Okay? So in principle, your simulation should be able to reproduce this behavior. And finally, as I was mentioning already, stellar feedback drives galactic outflows that modulate the stellar buildup of your system, will lower the gas fraction, and alter the chemical evolution of the dwarf galaxies. And so your simulation should be able to reproduce a huge amount of data that has been accumulated recently on, for example, stellar and gas metallicities in dwarfs. So we have recently run a high-resolution simulation using the SPH technique. I'll spend a bit more time on that. And I'll describe that. And again, not as a unique simulation. This is just representative of the new generation of simulation and what you can do if you resolve the physics of the interstellar medium and of outflows. 7 massive dwarfs in this field is a group of dwarfs. We were lucky. There were 7. We only looked at systems that are above 10 to the 8 solar masses or so. And so that made the naming convention easy. I'm going to show you in a moment. You see the field we simulated. This is dark matter. This is gas. Those are the 7 dwarfs that I'll be discussing next. It's a simulation in lambda CDM, cosmological SPH, run down to z equals 0. Just to give you an idea of what the typical resolution in stars is, about 1,000 solar masses per stars. In dark matter, it's about 10 to the 4. Okay, these are big systems. This one has got a mass, a dark matter mass of 3/10 to the 10. So you resolve those systems with several millions of particles. Okay, this is close to state of the art because the gravitational softening is about 86 parsec. That's our resolution. The hydro resolution is 10 times better than that. So you resolve pressure better than you resolve gravity, and you don't worry about spurious fragmentation. But this is a state of the art. Other people are doing similar type of simulations. So what you have to put in is metal-dependent gas cooling. As you change the metallicity, the cooling properties of your gas will be changing. You have to have heating and photoionization from an external ultraviolet background, which is changing the ionic abundances of primordial gas as well as metals. And so it will affect your cooling function. And then if you have high enough resolution, you can place a high star formation gas density threshold. In this type of simulation, as in others, stars are not forming as before when the medium became denser than 0.1 particle per cubic centimeter, which is the old threshold when you didn't have the resolution. You can start forming stars now because you resolve those regions at 100 particles per cubic centimeter, which is typically the typical mean density of molecular clouds. Okay? And again, at this type of resolution, you're close to resolving the Jeans mass for gas at 1,000 Kelvin or so.
So what total mass are we talking about here?
So the total of each system?
No, the total mass in simulation.
Oh, the total mass, well, it's probably dominated by this system. So this is 3/10 to the 10. There are a few by 10 to the 10 around. The total must be about 10 to the 11. But this is zoom in. This is the high resolution region. It is embedded into a larger region, which is run at low resolution, so you get the tidal field correctly. Okay? And it's in the high resolution region, which is a few megaparsec or so, where you put your gas and physics. Okay, I'm sure you heard a lot about different technique for solving the hydro and new codes. like Arepo, etc. These are SPH simulation, and I'm sure you know about this. I just wanted to highlight a few features of SPH. With SPH, you're resolving the mass distribution. You are discretizing the mass distribution as opposed to the volume. And SPH gives you an exact solution to the continuity equation. Resolution follows mass. And so the particle nature of the gas gives natural compatibility with n-body codes. There is, in SPH, zero intrinsic dissipation, numerical diffusion. Okay? That's good and bad. It's good because you don't have numerical effect. It's bad because you have to add it explicitly to form shocks and, for example, avoid suppression of fluid mixing. Okay? Some people think that's bad. Some people like the idea of having to put diffusions by hand because you have a better control of what's happening. Okay, so you get exact conservation of mass, momentum, angular momentum, entropy. Advection in SPH is done perfectly, which is important if you're after Galilean invariance. Again, this needs to be the case in simulation where you have highly supersonic bulk flows. SPH does not crash, and I'm telling you in case you want to run hydro simulation with SPH, SPH will not crash. If there is some screw up in your code, that will be indicated by noise rather than by crashing, okay, as opposed to AMR, which tends to crash all the time. More importantly for us, gas particles have names in SPH, meaning that they have an ID. If I see a gas particle today and in a host, in a Milky Way type of system, and I want to know where that gas particle was enriched, whether it was in the main host or in some satellite, I can easily do that because I can carry that IDs from snapshot to snapshot. Okay, that's extremely difficult to do in AMR. In fact, it's basically impossible if you have a grid code to understand exactly what's happening. Okay, and in fact, you will see that there is quite a bit of difference in interpretation of this simulation if you do SPH versus AMR. And again, I'm not an AMR guy or an SPH guy. I've run simulations with both type of approach. But these are the plus of SPH. Okay, there are new type of SPH, and this is old SPH. So this is the famous blob test, where you have a blob in the wind tunnel. It's an overdense region, which is moving at supersonic velocity. And the issue here is that old SPH, represented here by the gadget 2 codes, basically did not mix very well as opposed to new SPH or AMR. Okay, so the idea here is whether SPH is able to reproduce instabilities, Kelvin-Helmholtz instabilities, when you have dense blobs moving into a low-density medium.
What's the difference between lossless code and repo?
Yeah, so there is some degree of freedom in how you write equations in SPH, and so this formalism creates some spurious surface tension, and this doesn't. And this is true for all. Yeah, sorry.
The question was, what does a repo produce?
Oh, compared to Arepo is closer to this. An AMR code has got diffusion. It mixes the two fluids very well. So that's the idea. So people are changing SPH codes in order to get closer to results from AMR in that particular type of situations. Okay? So there is a tendency here to try to mix the gas extremely well. A word of caution, if you look at the Milky Way halo gas, it doesn't seem to be mixing particularly well. So I'm just worried that some of this new technique, which tends to mix gas in a background extremely efficiently, will not be able to reproduce the clumpy structure of neutral hydrogen, for example, in the halo of the Milky Way. Okay, and that's a test that people should try to use and look at in order to gauge their ability, the ability of their code to feed the data. Okay, that was just a technical comment. Feedback, well, as you know, there are 3 types of lies, and feedback is one of them. So what we do, and you heard quite a bit perhaps about this here, is we have only supernova feedback. So each supernova will deposit an energy of about 10 to the 51 ergs with a Krupa IMF into the nearest neighbors. We use a trick which is to shut off cooling for particles that are heated up by supernovae. And that's a trick that has been used for a few years. Let me explain what happens. In a real interstellar medium, you inject 10 to the 51 ergs into supernova ejecta. And the supernova ejecta for a 10 solar mass stars are just typically 1, 2 solar masses. Okay, so 10 to the 51 ergs into 1 or 2 solar masses will drive the temperature of that gas to 10 to the 7 Kelvin, 10 to the 8 Kelvin, where the cooling function is such that the cooling time is very long. Okay, that means that that gas in the real universe cannot cool, and all the thermal energy will become kinetic energy of the expansion. Okay, you create a blast wave, and that blast wave will propagate into the interstellar medium. Okay, that's nice. That's what happens in the real universe. Now try to simulate that. You have 10 to the 51 ergs. Now that 10 to the 51 ergs is not going into 10 solar masses particles because you don't have the resolution. You are dumping that energy into a gas particle that is typically 1,000 solar masses, 10 to the 4 solar masses. By conservation of energy, the temperature of that gas particle is not going to be 10 to the 7, 10 to the 8. It's going to be 10 to the 5, few by 10 to the 5. You are now at the peak of the cooling curve for gas. Okay, that means that that gas is going to cool immediately. Okay, very little of that energy goes into kinetic energy. You don't produce winds. Okay, that's true in every code. Okay, and every code deals with it in a different way. So the way we do it, it's a relatively easy way of doing it. And that is to say, we don't allow heated gas to cool down for the duration of a blast as taken from some self-similar solution of McKee and Oestreicher a long time ago. Okay? That's it. So basically, when a supernova is exploding, we don't allow the gas surrounding that supernova to cool down for a time scale that is typically about 10 to the 7 years. Ideally, it would only be for the adiabatic phase of the set of Taylor blast, but that adiabatic phase doesn't last long enough for our time resolution. Okay, so we cannot do that. We have to do it longer.
So why can't you mix in low mass particles? Because the coronal gas doesn't carry much mass. And you give the low mass particles.
I have a distribution of
How do you get low mass particles?
because of gravity and because you get a lot of spurious effect if you have multi-mass. You try to avoid multi-mass as much as you can.
It would have very different smoothing rates.
Yeah, that's right. And then you'll have to.
They all mix together, and how do you define the fluid?
It'd be a disaster.
Yeah. So ideally, in a few years, we'll be able to push down to a few solar masses. Then this problem will not occur because we will be dumping all the supernova energy into 10 solar masses instead of 1,000 solar masses. It's just numerical resolution that requires you to work on a recipe to try to get winds out of it. So in this way, we are able to produce outflowing blast waves which overlap and create large-scale outflows. And at a certain point, you have to say it's a trick. Then you look at what you get out, and you compare with the data and see whether you have the right prescription. It is minimalistic in the sense that it doesn't have a lot of free parameters here. In fact, we don't scale with the halo mass. We don't scale with age, with redshift, etc. These are just the properties of the local interstellar medium, the density, the pressure, etc. Okay? Other people prefer to put more stuff into it. We know there is energy being produced. This is the specific luminosity radiated by a stellar population as a function of age. This is the amount of energy that goes into supernovae. This is the amount of energy that goes into winds. This is the amount of energy that goes into luminosity. And so if you can tap some of that energy, for example, by wind driven by the absorption of photons by dust, for example, then there you have another feedback mechanism. But every feedback carries a number of free parameters. Okay? And I like to argue and it's a shame that Norm is not here, I like to argue that we have the least amount of free parameters to play with. We don't have explicit wind particles. We don't inject kinetic energy, just thermal energy. There is no mass or metal loading that happens automatically. We don't have two-phase subgrid ISM. These are all recipes that you'll find in the literature. We don't have radiation pressure on dusts. We carry the uncertainty of what is the optical depth to dust and whether radiation pressure is able to push your gas around effectively. There is no IGN feedback. Some people, to create winds, decouple the hydro. Okay? You launch particles and they're not hydrodynamically coupled with the rest, and so you produce ballistic winds. And then at a certain point, you couple back again, they shock, and you see what happens. Okay? All of this we don't know. We don't know and we don't do. Okay, that's the only recipe we are using. Okay, so let me tell you a little bit about the properties of those galaxies. I told you there were 7 dwarfs, which makes the naming convention easy. They range in mass between few by 10 to the 8 to few by 10 to the 10. Maximum circular velocity from 13 kilometers per second to 50 kilometers per second. Stellar masses change by about 3 orders of magnitude or so. And those systems are gas-rich, as we're going to see in a moment. Okay, so we seem to be forming the right amount of stars. So this is the stellar mass, virial mass relationship as inferred from what is called the abundance matching technique. Okay, I won't go into any detail, but this tells you basically, on average, if you assume a monotonic relationship between the mass of a dark matter halo and the stellar mass of a galaxy, it tells you pretty much what the star formation efficiency is supposed to be today as a function of virial mass. And that's that relationship here. Our 2 massive dwarfs are forming the right amount of stars there. They have star formation efficiency of about a few parts in 10 to the minus 3 or so. The other 2 dwarfs, which are not as massive as this, they have masses of order 10 to the 9 solar masses or so, are not forming very many stars. Okay, that's sort of different than what happened before. And what happened before is that you would be able to form star efficiently if you had a low mass threshold. We have a high density threshold for forming stars, and these low mass systems have problem in driving gas to those high densities, low temperature. Okay, so very few stars. You see how in this mass range, the stellar mass, the virial mass is changing by a factor of a few, but the stellar mass is changing by orders of magnitude. Okay, star formation becomes sort of stochastic on those mass scales. Sometimes it happens, sometimes the gas will be able to cool down and form stars, sometimes it doesn't.
So you're saying for that blue point, the dopey,
yeah.
If you waited a little while, it might go back up?
If I waited in the future, I think dopey, it's pretty much gone. I think if I rerun a similar mass with a slightly different accretion history, then this system might be higher.
You're saying it was too bursty earlier. So
It was bursty. Early, it's a shallow potential well. You remove some of the gas. Star formation is quenched, not very efficient there, okay? That's part of the issue. Another issue, of course, it's this stuff. It forms early, it's photoionized. Their gas is photoionized by UV background. It cannot cool down. There are no metals in the first place, so where do you get the metals for efficient cooling? In fact, what we see in some of these systems is that some systems are able to form star late because they accrete material that has been pre-enriched by a nearby dwarfs and then vented out. So that material has got metals, and so that gas can cool now efficiently. And it's only at late time you accrete metal-rich gas, that gas will cool down, you form stars. Okay? But there is an issue there about the ability of those systems to form star efficiently, which, it's what we want for the missing satellite problem. We tried to do a similar calculation using a different code just to see whether SPH versus AMR versus grid would give you any difference. And in fact, using even a different type of star formation prescription, which is regulated by the presence of H2. Okay, there's a lot of work has been done recently over the last few years about the properties of galaxies which are observed and detected in H2 and their ability to form stars. And so we use star formation prescriptions which are driven by the abundance of H2. And this is a larger simulation, larger box, where we have a lot of dwarfs. And of course, the price you pay is that your resolution is not as good as in this one. But this is, again, star formation efficiency, the ratio between the stellar mass and the halo mass as a function of halo mass. And you see high mass systems, Milky Way type of system here, or high mass dwarfs are able to form star relatively efficiently. And when you go down below 10 to the 10 solar masses or so, the star formation efficiency drops. Okay, these have been termed dark galaxies, not because they form 0 stars, but because they don't form very many stars. Okay, this is something that was not happening in past simulations. Okay, you need to have the resolution, you need to have the right chemistry to be able to map this transition. And we are far from understanding. This is high redshift. 2.5, again, the price to pay for the much larger box is that we have not been able to run this simulation down to z equals 0. So we don't know what the counterparts of these systems in the field are as z equals 0.
So for 10 to 10 solar mass halo, what determines whether it ends up in the low FH star pump or the high FH?
Yeah, it's assembly history. There is heating from early time, just from accretion. And then the issue... Well, the issue is, in this particular type of model, so you build H2 on metals, on dust. And so you need to accumulate a certain column density of metals for that to happen. And then you trigger star formation. And so whether these systems are able to forming stars or not is whether they were able to get to that threshold at very high redshift when the universe is denser, so they were self-shielded from the background, or whether they form late, fluffy, low column density, low metal abundances, very little stars. Okay, this is just to show you that below 10 to the 10, there seems to be a critical mass. Below 10 to the 10 solar masses, you can basically get all sorts of star formation efficiencies. So, okay, that's nice. We seem to be able to forming the right amount of star. At what price? Are those galactic outflows removing a lot of H1? So this is a plot of the H1 mass in those systems, neutral gas versus stellar mass, as a function of stellar mass here. And those are the 4 dwarfs in our simulation that are forming stars. And these are data, the gray points, are data from the alpha-alpha dwarf galaxy samples. Okay? Again, this is relatively recent stuff, just a couple of years or so. And what these people found, in fact, is that as you go to smaller stellar mass, okay, you get a higher H1 fraction. Okay, so it is not true that small systems are, for example, not forming stars because they removed all of their gas into the intergalactic medium. Dwarfs are gas-rich, okay? And our simulations are also relatively gas-rich. There is plenty of H1 left in those galaxies, in principle, to form stars. So this is just to tell you, to clarify one issue. Low star formation efficiencies in dwarfs are not the results of blowing away all the baryons. Okay? There is still plenty of H1 there. Baryons are retained, but they are not able to make stars because they are not able to get down to those high density. Okay, there is plenty of H1, it's just not 100 particles per cubic centimeter. So it's not able to form stars. If you use a different type of threshold, if you say stars form a 0.1 particle per cubic centimeter, then this system would be forming a lot of stars because there is still a lot of H1. It's just that resolution allows you to put stars in high-density clouds, and in these systems, there are not very many high-density clouds, so little efficiency of star formation. So you have to have feedback which regulates the thermodynamics of your interstellar medium. There is a lot of data on dwarfs that I was describing. One of that is to look at color magnitude diagrams of local group dwarfs and derive resolved star formation history, which are plotted there. This is work that has been done by Dan Weiss and collaborator. A lot of HST time has gone into producing those curves. Okay, so if you look at the stellar population of A dwarfs, what you find? What you find is that the average dwarf irregular in the local group, which are the systems that have gas, they form the bulk of their star prior to redshift 1. So this is 50%. This is the cumulative star formation history as a function of look back time. This is redshift. This is today. Okay, and this is 50%. So that, and each of these curves is a dwarf. So they are all over the places. But you can see that there is a trend that most dwarfs form at least 50% of their star prior to redshift 1. Okay, they're all systems. Okay, and so in fact are our simulation. In fact, if at all, our simulation are not able to reproduce the rapid rise in the stellar mass fraction at early time. Okay? Now, the error bars, this is still unclear. If you plotted error bars from this type of analysis at very early time, they are typically of order 1 giga a year or so. So you really don't know where to put those. But I would trust this plot all above, 11 giga a year maybe. The error bar should be small enough. Anyway, this is just to show that the star formation history that you predict from those dwarfs are in sort of relatively decent agreement with the star formation history that you infer from field dwarf irregulars. Okay, and this is just very quickly. We have the right amount of metals. They are metal poor. This is stellar metallicity, iron as a function of luminosity. This is gas metallicity, oxygen as a function of stellar mass. And again, the data are the gray point. The simulated point are the color one. Okay, surprising. Again, these simulations were not designed to fit this. We only have one of these simulations. We have not been tuning parameters to get this out. There is surprisingly good agreement between what you get with some vanilla type of simulation.
But if your explanation of this bimodality and star formation
yes.
is correct,
yes.
then there should be some bimodality in metallization, right?
No, and in fact, so let's look at that. What happens? It's an interesting point which we haven't explored in detail enough. People have played chemical evolution model to explain that trend, okay, which is the natural thing to do. And then you wonder, okay, is this mass metallicity relationship the result of low star formation efficiency or the result of ejecting a lot of metals out in the intergalactic medium, into dwarf medium or so? So our dwarfs have very different behavior. These types of guys are ejecting 90% of their metals away. So they are sitting here for their luminosity into the low metallicity regime because they eject most of the metals. These guys have not ejected a lot of metals because they don't form very many stars in the first place. They don't produce very many metals. And still, they're all aligned.
Well, I can see how one might explain the position on this curve.
Yes.
But you were showing bimodality
In the star formation,
mass.
yes.
And that had to do with H2 formation,
Yes.
which you were explaining was sensitive to dust.
Yes.
Which is very metallicity dependent.
Yes. And still, if I plot, so those are those four systems. You're seeing where they lie here. And this is stellar metallicity. They're basically on top of the stellar metallicity relationship.
I see. So yes. Right.
Okay? So there is a bunch of mechanisms that are self-regulating and allow you to be there, not by design. It just happened to be. Okay? I don't want to make a big deal, just to show, in fact, that this seems normal dwarfs. They look like dwarfs. in terms of stellar mass, H1 mass, and metallicity. Which brings me to the next part, which is, well, what are the structural properties? Okay, so we have a bunch of nice-looking dwarfs. We compare those with the data. If I were to plot the dark matter density of those dwarfs as a function of radius, what would I get? Okay, what I get is core, okay? What I'm plotting here is the dark matter density profile as a function of radius for 4 of those dwarfs. Bashful, which is the most massive one, with a stellar mass of 1.2 10 to the 8, dopey, grumpy. Okay? Now, to compare with some control simulation, we ran simulations, in fact, which were dark matter only. Okay? And those are the gray curve that you see there. So if I run the same simulation without gas, without star formation, without feedback, I get a Caspi density profile as predicted by NFW, for example. Okay? But once I run with gas, form stars, produce outflowing gas and winds, I get cores. Okay? So the hydro simulations here are always in blue. The CASP simulation are in gray. And you see a core on this mass scale. You see another big core on that stellar mass scale. On these mass scales, you don't see much of a core. Okay? Below 10 to the 6 solar masses, there is not enough energy input from supernovae to create a core dark matter profile. Okay? I can fit the dark matter distribution with the core in these two systems with a pseudo-isothermal distribution, and I get a core radius of 1.8 kiloparsec for dark and 2.1 kiloparsec for bashful. So these are large core, kiloparsec size cores in systems that are as massive as these two guys. Not much of a core here. The yellow stripe here is the region where I don't trust that our simulation has converged. Okay, we have a resolution of 80 parsec. About here, this is about 3.5 times that. So I wouldn't trust any result that it's on scales of less than 350 parsec or so, just because our softening is over the 80 parsec. But you see that in the most massive systems, you have a core distribution. So let's look at, yeah.
Less important in the,
sorry?
why is the feedback less important in the low mass systems?
Because you inject less energy, right, from supernovae. They're also lower mass, so you would expect the shallow potential well to help you there. But there isn't just enough energy from supernovae. You're not injecting enough energy. I'll show you a plot which shows you how the core size will increase depending on the amount of energy injected by supernovae. Okay, but basically there are not enough supernovae in this system to unbind the central cusp. Okay, they are too dark to create cores. Cores are only created in relatively massive dwarfs. They are massive, but they also have a high star formation efficiency. Yes.
Episodes
Yes.
for this to happen.
Absolutely. Absolutely. It's the entire cumulative star formation history. This is z equals 0. I'm going to tell you what happens in a moment, what happens as a function of redshift. Okay, in fact, next slide. So these are the two most massive systems, the one that have cores as z equals 0. And again, the gray is the collisionless simulation. The blue is the simulation with gas and star formation, the hydro simulation. And these are redshifts z equal 2, the dashed line, and z equal 1, the solid line. So the cores are already present at those early epoch. Okay, they're not late comers. Okay, they're not formed recently. They're old. Those galaxies, those dwarfs, were already cored at early time. So kiloparsec size core appears to form early. This is the core size now as a function of look-back time or redshift here. This is today. This is high redshift. For those two massive systems, again, the blue and the red curves. And you see the core size goes up to kiloparsec size scale very early, at redshift of 2 or so, they already have big cores, as seen here. And then the core appears to oscillate and keep growing on secular or long time scales.
And the halo mass was a symbol for that again.
The halo mass, no, you keep adding mass. I'll show you in a moment what happens to the escape velocity. They are still accreting material from the outside, okay? They are growing.
Oh, this is interesting.
Okay? These vertical lines, 4 vertical lines, are the redshift or 4 major mergers for the red curve, which is one of those dwarf galaxies. And you would expect perhaps that during a major merger, a lot of gas and dark matter is driven to the center. And if you have a core, that core will be replenished and you start with a cusp. And it doesn't happen. Okay, core seems to be resilient to major merger. You just see here, in fact, if at all, following a major merger, there is a burst of star formation and the core size goes up. Okay, but it never goes down to, that's our resolution. Okay, you create a core at early time, you keep a core profile. That core will withstand the merger with other subunits. This is a bit about the energetic. I'm going to go back to that. This is core size as a function of stellar mass. Okay, and again, this is 0.5 kiloparsec 1, 1.52. And you see within the resolution of our simulation, not much is happening below 10 to the 6 solar masses. As soon as you form more than 10 to the 6 solar masses, core starts to grow fast. A sort of threshold behavior. Okay, 10 to the 6 solar masses corresponds to about 10 to the 4 supernovae. Every supernova injects 10 to the 51 eggs. So we're talking about 10 to the 55, 10 to the 56 ergs are needed to evacuate a cusp.
That's not a resolution effect.
This one.
Yeah.
This might be. The flattening here might be. I'm just saying don't trust anything below there. But I'm just saying kiloparsec size core. Oh, no, this is well resolved. Okay, so what's happening here is these are just the two systems. Once you start to create a core, your potential is shallower anyway. It's not cuspy. And it becomes easier to enlarge that core. It's easier to enlarge a pre-existing core than to create it from scratch from a cuspy density profile.
And in the dark matter only simulations, the mergers are happening that's in a similar way.
Yeah. Yeah, but of course there were no cores that were all cuspy, etc. So they were adding material to the cusp. So let's go a little bit more into the energetics. What I'm plotting here is the total energy injected by supernovae. This is 10 to the 56, 10 to the 57 ergs in those systems. Again, as a function of redshift, this is 0, or look back time for those systems. And that's the solid curve there. And these points are delta W over 2, where W is the total gravitational energy of my dark matter distribution. So W is the integral of the dark matter density times the enclosed mass, which includes everything, gas and stars, etc. Integrated. And what we've done is compute delta W, which is the difference between the gravitational potential of the simulation with the core, which is dihydro simulation, minus the gravitational potential of the simulation with the cusp, which is the dark matter only simulation. Okay? So the difference in that gravitational potential must be due to the energy injection by supernovae. And the factor 1/2 comes from the virial theorem. Okay? So if I want to create a cusp, if I want to create a core from a cusp, I have to inject at least this amount of energy. Perfect coupling, perfect efficiency of 1 would require this amount of energy. Of course, I need much more than that. First of all, because I'm not coupling directly supernova ejecta to the dark matter. I'm removing the gas, and the gas is heating up, changing the potential, and changing the dark matter. And also because some of that energy will be radiated away. Yes, we have shut-off cooling, but once cooling sets in, that energy is lost from the system. Okay, so ideally in your system, you would like to have a situation which is exactly the one that we get in this simulation, is one when the energy injected by supernovae is always considerably higher than the energy required for that transformation. Okay? This is the minimum energy that is required from going to a Caspi distribution to a core distribution. Okay? And the ratio between the supernova energy that is injected and the minimum energy that I need for that transformation, it's about 30-40 or so. The efficiency is only a few percent. Only a few percent of the energy that I'm injecting into the system is going into creating such a core. The rest is either radiated away or goes into removing the gas as well, right? Which is how you change the global potential. Okay, so the energy injected by supernovae is typically larger than the energy that I need to create that core. This plot shows the escape velocity from the center as a function of time and perhaps sheds some light on what's happening. Okay, the hydro simulations are the solid line here, and the dark matter only simulations are the dashed line. So this is the central potential, or the square root of twice the central potential, which is the escape velocity. And you see that in a dark matter only simulation, the escape velocity from the center keeps increasing because mass is being added. This was to answer your question. Okay, those halos are still growing. But in the hydro simulation, once I create a core, the escape velocity from the center does not change much. Okay, I have a shallower potential. So even a small amount of energy at this late time will in fact enlarge that core because that potential is not as deep as it used to be, and not because there is outer mass missing. It's just the core itself has created this flattening. Okay, so once you start to create a core, and you see that in the other galaxy, again, this is dark matter only, this is hydro. Once you start to create a core, it becomes less energetically taxing to enlarge that core by removing material.
So how much of this is that you're merging together objects which are core, thereby producing something which is core?
Yeah, so at this late time, there is little merging. There is a lot of merging at earlier time. And yeah, so the issue is, people have tried to simulate that. The issue is if you merge something that is cored with something that is Caspi, which wins? Okay, and the answer is cores tend to be resilient and to survive major merger, which is also what we see here. Yeah.
Have you even looked at this level of detail with any other feedback prescriptions?
No, no. This is the first time we are looking with that feedback prescription. Now, the formation of cores has been checked with a different prescription and a different code. AMR, Romain Tessier, I used Ramses, and it was not even a cosmological simulation. It was a non-cosmological dwarf at higher resolution, a different prescription, but still tuned up to produce outflows, and it was able to produce core. But because it was not a cosmological simulation, it didn't have the entire history there available. So why are core produced in the first place? This is the star formation history of our dwarf. I told you it's extremely bursty. This is specific, it's not specific. Is it specific? Yes, it is specific star formation rate as a function of look-back time and redshift. And again, there are spikes, okay? Star formation occurs in burst. And what I'm plotting in this, I'm zooming into that period. A typical hydro simulation, you'll save a few snapshots, okay? And so you have a coarse time grid. So what we did to look at oscillations in the potential was to resimulate the same galaxy group at much finer time resolution. Okay, so the time resolution here, it's 20 mega-year or so. And this is the baryon mass within a radius of 500 parsecs. So this is the central baryon mass. 500 parsec is the solid curve, and 1 kiloparsec is the dashed line for the two simulations there, for the two dwarfs. Okay, this is time, this is redshift. So it's just a zoom in with a finer time resolution in that regime. And you see that there are fluctuations in the baryon mass at the center, which occurs on time scale that are much shorter than the dynamical time at that radius. Okay, these are non-adiabatic change in the potential. Okay, those spikes here, this. Okay, they are outflows that are occurring on time scale that are very short compared to the dynamical time. Non-adiabatic change in the potential. And there is a nice paper, if you want to read a nice analytical paper on what might be happening by Ponsen and Governato, which explains exactly what would happen in the case of a harmonic oscillator where you change the potential, when you change the potential non-adiabatically. And that's when the dark matter gets heated. If everything was adiabatic, gas would be accreted adiabatically, and you would steepen the dark matter profile. And if gas were then ejected adiabatically, you would go back to the initial profile, which is NFW. Okay, so adiabatic changes are not going to produce cores.
So I forgot the details of the paper, but the basic idea that there's an asymmetry. You got some adiabatic inflow.
You have adiabatic inflow and non-adiabatic. That's right.
And then the net result of the dark matter
That's right.
is to expand.
That's right. And not only that, but you do it multiple times.
Right. So it's a
Okay.
small asymmetry each time.
Yes, that's right. And you can see this happening here. Okay, there are large drop, and then it climbs again on slower time scale, and then it drops again.
And because the baryons aren't being expelled, you can repeat the process.
That's right. That's right. You repeat it. They don't go to infinity. They go into the halo, fall back in, and you have oscillations that heat up the dark matter. Very neat mechanisms that has been explained a posteriori, first found in simulations like this, but then found an explanation into that. Okay, this is my last transparency here. So what we've done here, okay, so there are cores. Core explains the observation of the dwarf satellites. I told you that cores are seen in the field. They're also seen in the dwarf satellites. There are two, in fact. These are satellites of the Milky Way. They are relatively massive in stellar mass. They have 3 × 10⁷ solar masses in the case of Fornax. Fornax is one of the most luminous dwarf spheroidals within the Milky Way. And Matt Walker and colleagues have found a way to use stellar dynamics of populations which have different metallicities. Okay? And so they are assumed to be independent tracers of the same potential to constrain the distribution, the mass distribution within the inner region of those dwarfs. This is 1 kiloparsec, so we are about 1 kiloparsec here. And both in the case of Fornax and in the case of Sculpture, they found that this slope, which is gamma equal d log m over d log r, has got a value that is between 2.5 and 3. Okay, now if you have a flat core, this gamma, in fact, would be 3. If the density is constant, then this logarithmic derivative is 3. If you have an NFW profile, gamma, it's 2. Okay? So these are the results. Again, it's a different way of looking at the same issue here. These are the results of our dark matter-only simulations. And you see, of course, there are typically NFW profile. They are steep profile. Gamma is less than 2. Once we put hydro in, star formation and outflows, those two galaxies have profiles that, in fact, appear to match the observations. Okay? So there is an explanation, and people have tried to explain this by a variety of mechanisms. So yes, there are cores. Perhaps galaxies, those dwarfs, the dark matter in those dwarfs is heated up by tides. Okay? There are lots of environmental effect when dwarfs get accreted into the halo of the Milky Way. I guess what we are arguing here is that you don't need that. You might still have that, but if those dwarfs are luminous enough, they will be accreted with a core because it is star formation that is producing and outflows that is producing those cores. Okay? let me conclude with a too big to fail problem, which I told you about. And again, so what happens, what is an easy way perhaps to look at too big to fail, is that if you take a simulated Milky Way size halo, you'll find that there are several massive subhalos with Vmax, the maximum circular velocity, which is just square root of gm over r. So it's a proxy for the depth of the potential of about 30 kilometers per second. Okay, this is an n-body simulation like Via Lattea, like stuff that you might have been used. Dark matter only. High resolution, you'll find a few of those subhalos that are massive enough that have these circular velocities. Now, because these are massive enough, you would expect them to be the host of the brightest dwarf spheroidal. Okay, high mass, high dark matter mass, high stellar mass, high luminosity. But in an body simulation, if you look at the circular velocity profile of this system in the central region of those subhalos, you find that those circular velocity profiles, like shown here, are typically much higher than the circular velocity that you infer in the central region of a bunch of dwarf satellites. So these are data, the points are data, okay, for a bunch of satellites from Leo 2 to Fornax, Sextans, Leo 1, Sculptor, etc., etc. You can look at stellar dynamics, get information on the circular velocity profile, you get those 2 points, several points as a function of radius there, the inner kiloparsec. And if I take my n-body simulation only and I look at the more massive systems, these are the rotation curves that I expect. This is bashful with a Vmax of 50 kilometers per second. This is Vmax of 38 kilometers per second. Vmax is reached, of course, a large radii, but because they have Caspi profile, their circular velocities within the inner regions are very high, too high compared to this. That has given origin to the too big to fail problem. Where are these systems? Why don't they have a counterpart in the bright dwarf spheroidals? They can be dark because they are too massive not to be forming stars. They are too big to fail. Okay, so this has been, claimed to be a massive failure of cold dark matter. Okay, it's all over the places.
What are the radii of these halos?
For the simulated one, 50 kpc or so. So it is reached.
There is a convergence between
Yeah.
the collisionless and the baryon.
Yeah, but it's just on large scale. Yeah, as it should be, right? So that's the n-body simulation. These are the same system. The red curve and the blue curve are the same system. They have the same Vmax, are large distances as we were claiming, but because they have cores and because they have those cores have been produced by star formation, their circular velocity profile are here instead of being there. Okay? They're not as dense as the n-body simulation because dark matter has been combed away, has been heated up. Okay? So if I look at this, I say, well, we don't have any too big to fail problem. Right? Those massive systems like this will have cores because they have produced enough stars that to hit the dark matter, the central region, by these oscillating potential mechanisms, and I don't see any evidence for that. So if you believe this type of simulation, and if star formation creates core in the most luminous systems, then you cannot use n-body simulation to look at the central region of dwarfs. You have to use hydro simulation, and those dwarfs are going to be less dense than the n-body simulation, in agreement with the observations. So let me conclude. Lambda CDM simulation of high resolution and hydro with outflows. In the case of dwarf galaxy produced realistic systems, that seems to compare remarkably well with the observation. We were surprised by this, I have to say. Okay, we started to simulate this thinking that we would get all sort of problems in CDM. We don't seem to find very many of them. The simulated dwarfs appear to be dark, bursty, cored, and gas-rich. Okay, their properties are strongly modulated by the depth of the gravitational potential well. we're trying to map this. Okay, we only have 4 simulated dwarfs with stars. The other 3 didn't form any stars. It would be nice to have a sample to map these properties as a function of mass. And we'll try to do that in the future. I said we had 7 dwarfs. 3 halos below 10 to the 9 solar mass stars are devoid of stars. They never reach density threshold for star formations of 100 particles per cubic centimeter. They don't form any stars. Do I believe that? Part of this, it's because of the impact of the external UV background. Okay, you don't have radiative transfer, so we don't self-shield that gas. I suspect if we had some self-shielding prescription, these halos would be able to form a few stars at early time. We are checking that. Okay, you can use some Sobolev approximation, which tells you what's the optical depth of your gases, and if the optical depth is too high, you say, well, that gas particle is too dense. Okay, it will self-shield. It's not photoheated by the UV background, and it will collapse. You can do that on the fly. So we are trying to run a simulation like that to make sure that that is the case. But remarkably, we find that there are plenty of dark galaxies, galaxies that form very little stars. That's also seen in AMR simulation with H2 regulated star formation. Galactic outflows don't eject all DH1. There is still plenty of H1 in those systems, but they seem to be ejecting preferentially metals. Okay, so if you are a fan of chemical evolution model, those outflows will produce subsolar yields, okay, and eject metals in the IGM to large distances. And that's something that we see. And again, there is plenty of observation now from COS and HST that probe the halo of those dwarfs by looking at quasar or other galaxies in the background and taking spectra. So that's another piece of information that we'll be able to add and compare with the observations. Within the limited size of our sample, LCDM simulations with outflows appear to simultaneously reproduce the observed stellar mass and H1 content, resolve star formation history, gas phase, and stellar metallicity of field dwarfs in the local volume. Dwarf galaxies that form more stars than about 10 to the 6 solar masses. And again, that's for the assumed IMF, which is Krupa. Okay, it's not top heavy. In principle, if you allow for a top heavier IMF, you can inject more energy per unit stellar mass, create cores even with less stars. But anyway, it's only dwarfs with M star greater than 10 to the 6 solar masses that develops kiloparsec size core. Because most of the dwarfs form of these stars prior to Z equal 1, they form most of these stars at high redshift. And the amount of work required for dark matter heating and core formation scales approximately as the virial mass to the 5/3. This is mass squared divided by the radius. Okay? So if you create cores at early time, when your halo has not grown up, okay, you gain energetically. It's easier. It's not as energetically taxing. People have done experiments in trying to produce core as equals 0 out of an equilibrium system, which is very massive. And of course, they require a lot of energy because that system has reached its final mass. It's supposed to be cuspy. Okay, and so you need a lot of energy to unbind that cusp. What we find is that the unbinding of the cusp starts early when the virial mass of your halo is much smaller. Okay, so it's easier at early time to start to creating cores. In other words, dwarfs are never cuspy. They are born, provided they form enough stars. At very early time, they create a core, and that core will keep increasing. Okay, you have star formation in a relatively shallow potential well. Okay, so the unbinding of the cusp starts early, and the formation of core profile is not as energetically onerous as previously claimed. This is the distribution of dark matter particle. This is just to show these are the two systems. They have virial radius of 50, 85. These are all the dark matter particles that have been ejected, that were once within 2 kpc. Okay? Dark matter particle, the particle in the cusp, are not ejected to infinity. They only go to 5 kiloparsec or so. twice the size of the core, 3 times the size of the core. So again, if you look at the energetics, you don't have to remove the cusp and move all that dark matter to infinity, totally unbind the cusp. You just typically move those dark matter particles to the halo, displaced to 5 kiloparsec on average. Okay, that makes the energetics simpler from some point of view. The supernova feedback is key to solve the too big to fail problem. We don't seem to find any issue with that. And so I know I'm being provocative here, but what's wrong with the dwarf galaxies in LCDM? We seem to have a good mechanism, which is baryons, that is able to explain a lot of the data, including their structural properties as well as their star formation properties. Does that mean that cold dark matter is the right theory? No. But I'd be reluctant to add more free parameters, like in self-interacting dark matter or warm dark matter, to explain a bunch of observations that, in fact, are explained by baryonic processes like the one I described so far. OK, that's it. Chris.
So what's your prediction about intensity masses as the star formation really sets in? Are you going to get us in the baryon injection?
Well, of course, at that point, yes. So we have not looked into that. We looked at 10 to the 12. We don't have anything in between. At 10 to the 12, you create a core still, but it's a small core, okay? 0.6 kiloparsec or so. If you go to those masses, star formation is not as bursty. So it's a Milky Way type of system. You look at the star formation history, it's sort of smooth. And so yes, there are outflows, but they are on longer time scale, and they're not repetitive as in the dwarfs. So my expectation would be that on that mass scale, you would not see much of a core. What's happening in between, and when that transition region is happening, I don't know.
One more question.
So, because there is a substantial amount of neutral gas in these dwarf galaxies.
Yeah, that's seen. That's observation.
Enough alpha you see it in nearby, in a very nearby sample.
Yes.
If you extrapolate this to cosmological abundancy, what on the H1 do you get out of that?
Yeah, that's a good question. As equals 0, I haven't tried that because I don't have enough of those systems. Okay, I can't make an omega H1. Let me put it that way. We've done that at high redshift, 2.5 with the ENSO simulation, and we were okay, but a little bit above what is inferred by looking at damped Lyman alpha system. You can get some estimate of the total amount of H1 in the universe at 2.52. And we had too much H1. Okay, not by huge factor, perhaps factor of 2 or so. It is unclear why that is the case. Okay, maybe it's a little bit more feedback. Again, it's not 1 dex, so it's something that can be fixed. But at least at 2.5, we are a little bit above what the observations are telling us is the total H1 content of the universe. As equals 0, there is much better information because you look at H1 survey, et cetera, but we don't have enough system to make an H1 mass function. We should, but that will need 200 type of galaxies like this, and we only have a few.
Okay, so we'll be taking Piero out to dinner tonight, maybe around 7, so please email me if you want to join.